Welcome to week 12, Transformers and Attention Mechanisms. This week, our day 1 will start with Introduction to Attention Mechanisms. Day 2 will be looking at Introduction to Transformers Architecture. Day 3 will cover Self-Attention and Multi-Head Attention in Transformers. Day 4 will be Positional Encoding and Feed-Forward Networks. Day 5 will be doing a hands-on with pre-trained transformers like BERT and GPT. Day 6 will be looking at advanced transformers, which are BERT variants and GPT-3. And finally, on day 7, we'll do a transformer project, which will be text summarization or translation. So let's get started with week 12. Welcome to week 12, where we'll be looking mostly on transformers and attention mechanisms. Today, day 1, we'll be looking at introduction to attention mechanisms. So first, let's talk about understanding the limitation of RNNs and the need for attention. So what are the challenges of RNNs? Again, so the RNNs is a topic that we covered last week. So if you are jumping directly into week 12, you would rather want to go over week 11 first. So to continue again, challenges of RNNs. First, sequential processing. RNNs process data sequentially, making parallelization difficult, which leads to long training times for large data sets. Next, long-term dependency problems. The struggle with learning long-term relationships in sequences due to vanishing gradient problem. Fixed context vector. The encoder-decoder structure of sec-to-sec models compresses all input information into a single vector, leading to information bottlenecks for long sequences. Now let's look at the role of attention mechanisms. Attention overcomes these limitations by allowing the model to focus on specific parts of the input sequence dynamically during each output generation step. Instead of relying on a single context vector, attention provides a weighted combination of all input tokens relevant to the current output token. Let's talk about the basics of attention mechanisms. First, the core concepts include queries, Q, which represents the current focus of the model. Example can be the current decoder state in sec-to-sec task. Keys, K, encoded representations of the input sequence. And values, V, additional information associated with the keys. Let's talk about attention mechanism itself. The attention score is computed using the dot product of the queries and keys followed by a softmax function to normalize into a probability distribution. The weighted sum of the values forms the context vector. Let's look at the formula. Attention of Q, K and V equal to softmax of Q of K raised to T divided by square root of dk times V. Next, let's talk about the different types of attention. We have self-attention. The query, key and value all come from the same input sequence, and it's widely used in transformer models for learning interdependencies within a sequence. Then we have a multi-head attention. Extends self-attention by applying multiple attention mechanisms in parallel. It captures different aspects of relationships in the sequence. The multi-head attention looks something like this, where multi-head of Q, K and V equal to concatenation of head 1, head 2 all the way to head H, W of O, where each head computes attention with different learned projects of Q, K and V. Now with all this information, let's jump into our hands-on exercise, where the objective is to implement a basic attention mechanism using NumPy or PyTorch and visualize its impact on a simple sequence task. So I'm going to do both this time, NumPy and PyTorch. So let's go ahead, and first step is implement a basic attention mechanism using NumPy. So go open a new file, save it as day1 underscore NumPy, and here let's start with importing NumPy first. Next, I'm gonna write the Q, K and V, which are define the queries, keys and values. So for that, let me just write it down here. Define queries, keys, and values. To do that, I'm going to say queries equal to np dot array, and this I'll give a 2 by 3 matrix 1 comma 0 comma 1, and next row the value says 0 comma 1 comma 1. So this is my 2 by 3 matrix for queries. Next is my keys. For my keys np array, this will be a 3 by 3 matrix 101 1 1 0 and 0 1 1. Okay, this is my 3 by 3 matrix for query. The next one is for values. It's 3 by 2. So I'm gonna copy, actually let's copy this. So this one, as I mentioned, it's values np array equal to, let's call it 10 comma 0 first element, second element I'm going to say 0 comma 10, and the third element I'll call it, since these are keys, I can say 5 by 5. Perfect. So this is my 3 by 2 matrix. Now let's go ahead and compute attention scores. For this, scores equal to np dot queries comma keys dot transformed. So there you go. So this will be giving us queries, which is a 2 by 3 matrix. Okay, I think I misspelled queries here, so oops. There you go. Perfect. Next, I'll go and apply soft max to normalize scores. If you remember the formula that we looked at, if not, you can just always go back a few minutes and you'll see the formula. Softmax of x will be exp underscore x equal to np dot exp x minus np dot max of x comma axis equal to -1, and keep the dimensions equal to true. Again, so this is first get me exp exponential of x. Then next I'm going to go ahead and return with exp underscore x divide by exp underscore x dot sum of axis equal to -1 comma keep dims equal to true. Again, if you want to look at this how it works, you can always go back to the formula and see what I'm doing here. Just applying those formula here. Now attention weights is another thing that I need. For that I'm going to say softmax of scores. So this will call the softmax along with the scores and give me my attention weights, which will be a 2 by 3 matrix. Now I'm going to go ahead and compute the weighted sum of values, which will give me all the things that I need. So context equal to np dot so this is my final formula, which will take attention weights and the values which are passed, which will give me a 2 by 2 matrix. So now let's go ahead and print first the attention weights slash n attention weights, and then I will print the context vector slash n context. Now all the formula is based on the formula that is defined by it, but if like this is the basic formula for basic attention mechanism, but if there is some typo or something, then we can't help it. So let's go ahead and open terminal, and I'm going to say Python, the file is called day1 underscore numpy, run it. And as I mentioned, if there is some typo that we have done, I have to make sure that I don't do any typos. Clear, run it again, and there you go. We have our attention weights based on the inputs that we have given, and this is the context vector which we get. So again, typos, I can't help it, but again the values are here. So this is based on the formulas that we spoke about earlier, and this is using NumPy. Now if I want to do the same thing using PyTorch, create another file and I'm going to call it day1 underscore pytorch.py. In here, first let's go ahead and import torch. Next I will go ahead and import torch.nn.functional, where we have all the functions, and there's I will get the f. Now first let's go ahead and define queries, values, keys and values. So I'm going to go ahead, copy this and define keys and values. So for queries, I don't use this. I will have to use, since I want a tensor, torch.tensor, and 1.0, it needs in float, 0.0 and 1.0, 0.0, 1.0 and 1.0. This is a 2x3 matrix. Next, for keys, I'm going to do the same thing. Torch tensor again, 1.0, 0.0, 1.0, 1.0, 1.0, 0.0, 0.0, 1.0, and 1.0. So this will be a 3x3 matrix. Then for values, again, I will say torch dot tensor 10 point 0, 0.0, then we have again 0.0, 10.0, 5.0, and 5.0. So this will get me my queries, values, and keys. Now first step was to compute attention scores. Now to do that, in PyTorch I can just say torch dot mat mul. The formula is to multiply queries and q of t, which is queries and keys dot transform. If you remember, that's what we used here. So same thing, we'll do it in PyTorch using this keys. Okay, perfect. Next thing is to, here in PyTorch we'll have to use softmax, apply softmax to normalize scores. So here we called the softmax function and then we did this. In PyTorch I'm going to say attention underscore weights equal to f dot softmax, because PyTorch already has softmax in here, and all I have to do is pass the scores and say dimension equal to -1. It will give me a 2x3 matrix of attention weights. Next I want to say compute a weighted sum of values. This I can get the here context equal to torch dot matmul. If you see, what we did here was np dot attention weights and values. So same thing, I'm going to say attention weights and values. So this will give me my 2x2 matrix. So now I'm going to go ahead and print again something similar that we did here, attention weights and context vector. And since my variable names are same, I don't have to change anything. Perfect. So this is how you do it in PyTorch. Now let's go ahead and check it out. I'm going to say day1 underscore PyTorch. And there you go. We have a tensor. If you look at the values, it's almost close. It should be the same, almost same to each other. And that's what you get. Now next thing is, if you want to visualize these attention weights, I can always use import matplotlib.pyplot as plt, and then visualize attention weights. Now to visualize attention weights, I'll say mat show, and I'll give the attention weights here. Next I am going to say plot dot color bar. Next I'm going to say plot dot title attention weights, and plot dot show. So this will show our plot for attention weights. So let's go ahead and run it. So I'll say Python day1 underscore PyTorch, and there you go. We have our attention weights displayed in a plot, nicer matte show type of plot, and that's what we see here. So I hope you were able to follow along with this, and if not, if you had any issues or have any questions on implementing any of these, let me know. We went and got our attention calculation. We computed attention weights and context vectors using a simple implementation in both NumPy and in PyTorch. And to summarize, today in day one, we understood the need for attention mechanisms to address RNN limitations. We learned the basics of attention, including queries, keys, and values. We gained practical experience implementing attention mechanisms using both NumPy and PyTorch. Finally, visualized and interpret the role of attention in sequence modeling. So if you had any issues or have any questions, let me know in the messages and I'll get back to you. Day 2. Introduction to Transformers Architecture. Today, let's start with overview of transformer architecture. Now, what is a transformer? A transformer is a neural network architecture introduced in the paper Attention is All You Need, and it relies entirely on the attention mechanism to process sequential data without using recurrence or convolution. It is transformative for NLP tasks like translation, summarization, and text generation. Let's look at the different components of the transformer. We have encoder, which processes the input sequence and generates a contextual representation. It consists of multiple identical layers, each with first self-attention mechanism, which captures dependencies between all input tokens, and feed-forward neural network, which is FFNN, which processes the attention outputs. Next, we have the decoder. It generates the output sequence one token at a time, and it consists of multiple identical layers, each with a masked self-attention mechanism which prevents the decoder from attending to future tokens, and encoder-decoder attention, which attends to encoder outputs, and we have the feed-forward neural network. Now the workflow for this is input sequence comes in and gets through encoder, next to the context vectors, next to a decoder, and finally you get the output sequence. Now let's go over the detailed breakdown of the transformer model layers. First, we have the self-attention layer, which captures relationships between all tokens in the input sequence. It then computes the importance of each token to all other tokens. Next, we have the position encoding. Since transformers lack recurrence, positional encoding injects information about the token order into the model. Next, we have the feed-forward neural network. It applies a position-wise FFNN to the outputs of the attention layer, and nonlinear transformation enhances the representation. Layer normalization stabilizes training by normalizing inputs within each layer. Finally, the multi-head attention. This combines multiple self-attention mechanisms to learn various aspects of the relationships within the sequence. Now let's look at some of the key differences between transformers and RNNs. As per the aspect of parallelization goes, transformers are fully parallelizable, faster training. RNN is sequential processing limits parallelization. Next, as per long-term dependencies, transformers handles long dependencies via attention, whereas RNN struggles with long dependencies. For position information, transformers uses positional encodings and RNNs implicitly encode its position. For architecture, transformers are built on attention mechanisms, so no recurrence, whereas RNNs have sequential processing through hidden states. Next, with all this information, let's jump into our hands-on exercise. The objective here is to visualize the architecture of a transformer model and set up an environment for working with transformers using PyTorch and TensorFlow. So let's get started, and first we'll visualize the transformer architecture. So this is a fun project. You might need some libraries installed. I already have things installed. I will keep this open to my day 2 folder, and here First, let's go ahead and add the visualization code. So I'm going to call this visualization day 2. It's okay, the spelling mistake, I can't run away from that. So first I'm going to say TensorFlow dot keras dot utils. I will import something called as plot model. Now this needs a bunch of additional libraries, so if you get any warnings or errors, it will probably tell you what you need to install. Next I'm going to say TensorFlow dot keras dot models. I will import from here model. Next, from TensorFlow dot keras dot layers, I will import input dense and layer normalization and add and multi-head attention. Perfect. So I have everything that I need here. Now with this, first let's define a simplified transformer block. So for that, let me call out what I'm doing. Define a simplified transformer encoder block. Okay, so let's start with the function. I'll call it transformer underscore encoder. I'll pass it input dimensions, which is input dim, and then I'll pass it number of heads that I want, and then I'll pass it the ff dim dimension, so feed forward dimension. So that's what I've passed. Now here, first I'll say input will be input of shape equal to none and input underscore dim. So this will be displayed as the input dimensional. Next, let's say for a multi head self attention, I'm going to first start with a variable called as, I'll call it attention output, which will be equal to multi head attention number of heads equal to number of heads that we got from the parameters. Next, I'm going to say key underscore, and the parameter needs is key dimensions, which I will pass it as input dimension. So that's the start of it, and then I'll say inputs comma inputs. So this, I think I named this as input instead of inputs. So those are my inputs. So that is what I passed there. So that's my first attention output. Next, attention output, I will go and add another layer. In this case, I'm going to add inputs. This is my residual connection, so that's why I'm using add inputs and attention underscore output in the previous one. So this will create my residual connection, and then finally again I'll say attention output equal to layer normalization, and inside this I will pass the attention output. So we have our multi-head self-attention. Once we have that, the next thing that I need is the feed forward neural network. So feed forward neural network. Now for that, I will first create ff output parameter, and first layer is the dense. We'll pass the ff underscore dimension that we have passed. Next, I'll use activation equal to ReLU, and I'll pass bandwidth of attention output. Next, I need another layer, ff output equal to, I'll say dense, and then to this I'll pass input dim of ff output. Perfect. So this will create my ff output. Next, I need outputs, final outputs equal to, I'll say add, what layers am I adding? First, the attention output from above, and then I need ff output from here, from the line number 15 above. So this will be my residual connection again. And now finally outputs equal to layer normalization. I have to normalize everything for outputs. There you go. So this can return back now finally model with inputs and outputs. Perfect. So this will have my entire transformer encoder block inside it. Now, if I want to plot it or visualize it, so I'm going to say create and visualize that simplified transformer, and so a sample transformer encoder block. So what I'm going to do in this particular case here is, first let me fix this, create the encoder block. Now to create the encoder block, I'll have to call that function. So I'm going to say transformer encoder. I'll pass some values. I'll say input dim equal to, let's say, 64 dimensions. I need number of heads equal to 8. And then I'll say feed forward dimensions of equal to 128. And then I can plot this model using plot model function that we have imported. And I'll say, I'll pass it, it needs the encoder block. I'll say show the shape. There's a parameter called as show shapes, and that I'll say true. And then to where do I want to save it? I'll say to a file called as transformer underscore encoder.png. So kind of when I save this and run it, it will create an image and save it on my folder. So that's why I have also the folder open here. This is my app, this is my code here, code file that I have here, and now I have nothing over there. So I'm going to say Python visualization underscore day2, run it. It's going to run through that code. If there's no typos, hopefully everything will be good, and create an image right here with the encoder transformation, with the transformer encoder block definition. And there you go. It took a minute or so, and then finally we have the visualize transformer encoder image here. I can open it, and as you can see, it shows the input layer with the output size of none 64. Then we have multi-head attention, and we have added layer normalization, dense we've added, finally added these together, and layer normalization. Based on the code that we have written here, it has created a visualization for me from that. So I hope you were able to follow along, because our next step is to set up an environment for transformers in PyTorch. For this, I'll have to go to my terminal, and first let's clear this out, and first install torch vision and transformers. If you have not installed already, these are the things that you need to set up the environment. So I'm going to run this, and it will run very quickly because I've already installed most of it. And then let's write a code to see if it works. I'm going to create a new file, save as day2 underscore exercise 1.py, and here first from transformers I am going to import bird tokenizer and bird model. Now these are some of the pre-trained models, so I'm going to say load a pre-trained bird tokenizer and model. To do that, first let's get the tokenizer equal to bird tokenizer that we have imported from underscore pre-trained, and the one that I'm interested in is bird dash base dash uncased. Okay, so that's my tokenizer. Next I'm going to say model equal to bird model. From that I'll say from underscore pre-trained, I want to get the pre-trained model, which is bird dash base dash uncased. So this will give me my tokenizer and model. Now let's go ahead and tokenize a sample input. So I'm going to say tokenize a sample input, and this will be text equal to transformers are powerful models for NLP tasks. That's what I'll say. Now I have that. Now I'm going to create an input equal to tokenize this input, where I'll pass this text that I've created, and I'll say return tensors tensors equal to PyTorch tensors. So I can specify which one I want. So I'm saying return me PyTorch tensors, and then I will pass the input through the model, and for that I'll create an outputs which will say model. I'll call the model function, and to that I'll give the inputs. There you go. And now I can say print hidden states shape. You can also go and visualize these things, but I don't want to go that far. You already saw how to visualize. I'll just say last hidden state dot shape. So just give me a shape of the last hidden state from the outputs. So that's what I'm doing here. I can go to my terminal and say Python, and this file is called day2 underscore exercise 1. Run it. I've not used most of the functionalities here because I'm just doing tokenizer model. So even if it gives me warning, that's normal. And there you go. We have hidden state shape torch dot size 110,768. So this is the shape of the last hidden state, and this is how we implement in PyTorch. Now, to do it in TensorFlow, first make sure that you have the TensorFlow installed. So we have already done a lot of projects in the previous week, so you should have it. So I'm going to say pip install and TensorFlow. I assume you have the TensorFlow installed. If not, okay, I think I spelled it wrong. TensorFlow, and there you go. It will have my TensorFlow installed. If you don't, then just go ahead. It will take some time to install. I'm going to call this day2 underscore exercise 2 dot py. In this case, since we need from TensorFlow, so I'm going to say from transformers, I want to import tf BERT model and BERT tokenizer. So I'm going to go ahead and take much of the same code from here, and I need the BERT tokenizer. I don't need the BERT model. I need TensorFlow BERT model. Now first is pre-trained BERT model and tokenizer. So I'm going to say tokenizer BERT model from pre-trained. This is what I need, and this is for TensorFlow BERT model from pre-trained BERT base uncaged. Next I'm going to say tokenize the input, transform, same stuff I'm going to give tokenizer. Now this is not PyTorch. I'm going to get TensorFlow, so I'm going to say change this to TF. Pass the inputs, outputs equal to model of inputs, hidden sample states, output last hidden state dot shape. So save this and go ahead and run it. Python. It was called day2 underscore exam exercise 2 dot py. Now again, as I mentioned, if it gives me some warnings because I'm not using a lot of things inside these, so that's understandable. And as I said, some weights of PyTorch model were not used because I'm not using PyTorch here. This is expected if you're initializing tf-BERT, and it tells you why it does that. And anyway, at the end, this is what I'm interested in. Hidden state shapes 110,760, almost same as the PyTorch one, and that's what we get from here. And that's now your environment is ready for both coding in TensorFlow and PyTorch. So I hope you were able to follow along. If you had any issues implementing this, let me know right now, because we'll be using this quite a lot throughout this week, and it's better to get clarity, or if you can search and see what the issue is, that can also help you into moving into the next steps. But if you had any issues and you want some guidance, let me know in messages and I'll get back to you. So just to summarize, today we understood the structure and components of transformer models. We went over and learned the differences between transformers and RNNs. We gained experience visualizing and setting up transformers in popular frameworks, and we built foundational knowledge for advanced transformer models like BERT, GPT, and more. So again, if you have any questions or had any issues, let me know and I'll get back to you. Day 3, self-attention and multi-head attention in transformers. So let's start today with self-attention mechanism. Now, what is self-attention? Self-attention allows a model to dynamically focus on different parts of an input sequence when encoding a token. It captures dependencies across all tokens in a sequence, enabling context-aware representations. The steps involved in self-attention includes first, compute attention scores, where you calculate the dot products between the query Q and key K vectors for all tokens. Then you scale by the square root of the key dimension dk to stabilize these gradients. Then you apply the softmax function to convert scores into probabilities and weight values. Use the attention scores to compute a weighted sum of value v vectors. And that's what we did in the last one, but we're going to go more focused today in the hands-on exercise. So these, remember these, and also the formula. Attention of qkv equal to softmax of qk raised to t divided by square root of dk times v. Next, we have multi-head attention. What is multi-head attention? Instead of a single attention mechanism, multi-head attention applies several attention mechanisms in parallel, and each attention head focuses on different aspects of the sequence. The steps involved here is linear projections first, where you project Q, K, and V into multiple subspaces using learned weight matrices. Then you apply self-attention. Perform self-attention for each head independently. Then you concatenate outputs, combine outputs from all the heads. And then final linear projection. Project concatenated outputs back into the original dimension. So multi-head QKV is equal to concatenation of each and every head W of O. Now let's talk about the applications of multi-head attention in NLP. First, machine translation. It captures dependencies across languages for better translations. Text summarization. Identify some key phrases to generate concise summaries. And named entity recognition. Focuses on contextual clues to detect entities in the text. With all this in mind, let's jump into our hands-on exercise, and the objective here is to implement a simplified self-attention and multi-head attention mechanisms and visualize their effects on text sequences. Now, if you want to implement this, you have to remember these formulas that we did in the last few slides. So if you want to cross-reference, always cross-reference or take a screenshot of it, and then you can look at how to implement the code. So first step is to implementing the self-attention mechanism. For this, I'm going to go ahead and start with a new file, save it as day3 underscore exercise, and save it here. So first I'm going to get import numpy as np. Let's go ahead and define query, key, and value matrices. For this case, what I'm going to do is I'm going to create a function, say generate data, and this will take our sequence length and embedding dimension. These are the inputs for this generating data, and here I'm going to say np.random.seed of 42. The reason I'm setting this again is to make sure that I get the same random data every time I run this. And then I'll say return np.random.rand sequence length and embed dim. So dimensions of how you want the data to be. So now let's go ahead and create a sequence length of 4 for this. Then I'm going to say embedding dimension equal to 3. So this is what I'll pass to the generate data. Now let's go ahead and get the query where, sorry, the Q parameter or Q variable, where I'll say generate data and pass it the sequence length and embedding dimension that I've created above. For key, I'm going to do something similar. Generate data, the sequence length and embedding dim. And for value, I'm going to do the same thing. Generate data and pass the two parameters, sequence length and embedding dim. So we'll get the Q, K, and V parameters now. Now next step is to go ahead and compute the attention scores. Okay, I'll move this up. To compute the attention scores, we can say scores if you look at the formula, that is pretty much multiplication of two matrices. One is query and key transform, so that is key dot t. So that divide by np dot square root of embedding them. Now, where do I get this from? Again, if you go back to our slide on single attention mechanism, here soft q k transform divide by square root of d of k. So that's what we are doing here. Our next step is to apply softmax to normalize the scores. So that's what is softmax of this. So for that, I am going to say create a function. First of all, softmax. Now this is not available with NumPy, but with Torch it was. So I'm gonna create that softmax function. Exp of x equal to np dot exp of x minus np dot max of x comma axis x comma axis equal to -1. I have to set up. Next, I need the dimensions to keep dims equal to true. So that's my first. Next, this will return the softmax of whatever parameter that we passed by expx divide by expx dot sum of, I will pass axis equal to -1 and keep dims equal to true. Perfect. So this will give me my softmax. So I need to get the attention underscore weights equal to softmax of scores that we have. So this line number 22 pretty much does this softmax of the scores that we have. The next step, as you can see here, I need the multiplication of this softmax times v, which is the value. So for that, I am going to say compute the context vector. So that is context equal to np dot multiplication of the two matrices, which is attention weights, whatever I got above, and value. So this will give the context, which is attention q kv softmax of this times v. So I have that here. So let's go ahead and print attention weights on the data that is generated. I'm going to say attention weights. Right, so I have that. Next, I can also print the context text vector, that is comma context. Right, so I have my attention weight and context printed out. I can go and open my terminal, and here I can say Python day 3, and there you go. We have our attention weights and we have context vector based on the random array that is created, and we'll get our context vector here. Now, if you want to implement a multi-head attention mechanism, and I want to use PyTorch this time, so I can just keep on writing here. I can say import torch, and I will import torch dot nn, and nn also I need the mf, so that is coming from import torch dot nn dot functional. I will import import as f. You can directly use functional. Now that I have that, let's create a multi-head attention class. So I'm going to call it multi-head attention. Now if you remember, our multi-head attention looks like this, multi-head of all the concatenation of all the heads. So for that, create this pass the module as usual. I will go ahead and initialize, call the initializer, create the initializer method. I will pass in here self and embed underscore dim, and I will pass number of heads that I want, and then I'll call the super with my multi-head attention and self dot underscore underscore init and call that. So I'm calling the super function here. Next, I will go ahead and say self dot embed underscore dim equal to whatever was passed to me. So embed dim self dot number of heads is equal to number of heads that was passed. Next, self dot head underscore dim equal to, from this embed dim uh, slash slash number of heads. So that will give me the head dimension. Now let's go ahead and assert embed underscore dim mod number of heads equal to 0. Then I will give a message saying, oops, embedding dimension must be divisible by number of heads or else it's invalid. So that's what I'm going to specify here. So once that is done, our next step is to say self dot query. So let's get the query first, the q parameter, nn dot linear embed dim comma embed dim. So that's the first step. Next, for the key is equal to nn dot linear, and that is embed dim comma embed dim. Perfect. Next, our value self dot value equal to nn dot linear, oops, not this, linear, pass it, same thing, embed dim comma embed dim. And then finally self dot output layer equal to nn dot linear embed dim comma embed dim. So that's good. So now let's go ahead and create the forward function, which will take self and x as input parameters as usual. And here let's first set the batch size. So I say batch underscore size, that will be always whatever the x size is, x dot size of 0. Next, let's go ahead and do the linear projections. So to do that, I'm going to say q equal to self dot query, pass it the value of x dot view. I'll have to pass the batch size and -1 for the second parameter. So next, I'm going to say self dot number of, I'll pass the number of heads it has, and then I'll pass self dot head dim, and then I'll say transpose this 1 comma 2. That's the parameters. Okay, so that's our first, that will give us the q. Same thing I'll have to do for k and v. So I'm going to go ahead, copy this, and I'll say k and v. So self dot, this time not query but key of x dot view batch size -1 self num, so all stay same, self dot value for v dot view. So this kind of gets us q, k and v. Now next step is to compute the attention scores. To do that, I'm going to say scores equal to torch dot mat multiplication or matrix multiplication, where I'll pass the value of q, k dot transpose, if you remember the methods, k transpose -2 comma -1, and then divide by np dot square root of self dot head of head dimension. So if you don't remember, you can go back to the formula and look at it. But again, I'm going to go ahead and calculate the attention weights equal to f dot softmax, pass the scores, and it was a scores comma dimension of -1. Perfect. So this will give me my attention weights. Now let's go ahead and compute the context. To get the context, I'm going to say context equal to torch dot matmul and get the attention weights comma v dot transpose 1 comma 2 comma dot contiguous dot view batch size comma -1 comma self dot embed dim. So this will give me, let's go all the way, context for the entire thing, and then now let's go ahead and return our self dot out and pass the context and attention. So that's my forward function. Now let's take some sample input and run through this. So I am going to say sample input. I will say sequence length equal to 4, or I also give embed dim, both of them together in the same line. My sequence length is 4, my embed dimension is 8, and I'm going to say x equal to torch dot random 1 comma sequence length and embed dim. Perfect. And now let's go ahead and instantiate and test this. To do that, first I want, let's say, MHA equal to multi head attention. MHA stands for multi head attention. The embed dim, and I'll need number of heads. I'll specify number of heads as 2 for this. Context comma attention weights, WEIG attention weights, or I'm not going to use the same parameter. Therefore, attention weights equal to MHA of x. So I'm going to pass this MHA of x, which multi-head attention, which will call this class, pass it, and give me here context and attention weights outside. So that's good. So I have everything that I need. Now let's go ahead and print attention weights slash n and pass it the attention weights. I don't know why I called it this. I'll remove the e, and then next I'll say print context vector equal to slash n of context. Perfect. So I have my entire code. I'm going to go ahead and mute these two guys. I don't need them, but I'll show this thing. So I'm going to go ahead and run, first clear it out, run my day 3 exercise 2. I think I have some matmul instead of, I'll use as usual, I've done some typos. Matmul, clear this out, run it again. One more transpose is spelled wrong. Let's go ahead and try this. And there you go, we have our attention weights and context vector. Now if you want to visualize this attention weights, I can always go ahead and import matplotlib dot pyplot as plt, and then inside this, let's say I want to visualize attention weights for a single head instead of multiple heads. I just want to see it for single head. Okay, so for that I'll say plot dot mat show, and this I'll pass the attention weights of the single head. So I'm going to say 0 comma 0, and I'll say dot detach dot numpy, so I can get my numpy data here. CMap equal to, I will use a colorful one, so I'm going to say viridis is what I'm going to use for this display. I'm going to say plot dot color bar is my display, and then I'll say plot dot title. I will give it as attention weights for head 1. I picked the first head, that's why. You can kind of change that and see whichever head you want to see, because we have 2 heads right now only. That's what we have specified, but I'm looking at the first head. So I'm going to go ahead, clear this out, run it again, and there you go. We have our attention weights head one figure here, plot for that, so you can visualize that and see the differences. So, to summarize, today we understood the mechanisms of self attention and its role in sequence modeling. We learned how multi head attention extends self attention's power, and we gained practical experience implementing and visualizing these attention mechanisms. We understood applications of attention in modern NLP tasks. So, if you have any questions or had any issues while implementing this, let me know in the messages and I'll get back to you. Day 4, Positional encoding and feed forward networks. So let's jump into understanding the role of positional encoding in transformers. Now, why positional encoding? Unlike RNNs, transformers do not process sequences sequentially. They process all tokens in parallel. Now, transformers lack inherent knowledge of token positions, which is crucial for tasks like translation or sequence modeling. What is positional encoding? Positional encoding introduces information about the order of tokens in a sequence. It allows the model to differentiate between identical tokens in different positions. Let's look at mathematical foundation and implementation of positional encoding. So first, let's look at sinusoidal positional encoding. It encodes positional information using sine and cosine functions. The formula for positional encoding is PE of pos or position of 2i equal to sine of position divided by 10,000 raised to 2i divided by d, and PE of position of 2i plus 1 equal to cosine of position divided by 10,000 of 2i divided by d, where POS is position of the token in the sequence, I is the index of the embedding dimension, and d is the total embedding dimension. Now, why use sinusoidal functions? It provides unique encoding for each position and allows generalization to longer sequences not seen during training. Let's talk about the feed forward network next. What is a feed forward network? FFNs are fully connected layers applied to each token independently and identically within a transformer layer. It adds non-linear transformation to the output of the attention mechanism. What is its role in transformers? It captures token specific transformations and enhances representational capacity. Let's talk about the structure. We have first the linear transformation, then we have non-linear activation, which is we use ReLU, and another linear transformation. So FFN x equal to ReLU x of W1 plus B1 times W2 plus B2. With this in mind, let's jump into our hands-on exercise where the objective is to implement positional encoding and integrate it with basic transformer model. We will also experiment with different positional encoding methods and observe the effects. So let's go ahead and start with a new project. I'm going to save it as day 4 underscore exercise. And first, we're going to go and implement positional encoding. So for that, I'm going to say import numpy as np. Next, I'm going to import, since we want to display the data, I'm going to use matplotlib.pyplot as plt. Next, I'm going to go ahead and define positional encoding function. So to do that, I'll create a function called as positional encoding, and it takes input as sequence length and embed dimension. Now inside this function, I will first get the position, which is POS equal to np dot range, and pass the sequence length to it along with uh, the dimensions from np dot new axis. So that will give me my position. Next, I'm going to say I equal to np dot range and pass it embed dimension. For this, I'll use from np dot new axis to end. So next I'll get the angle rates. So angle underscore rates, which is from the definition, if you remember the formula, 1 divided by np dot power. So I mentioned 10,000. Make sure we have all the zeros, comma 2 times. Let's make sure they're visible. I slash slash 2. So I have that, and divide by np dot float 32 of embed dimension. So as per the formula, this will give me the angle rates. Now I'm going to say angle rate rads equal to position times angle rates. So that will give me my angle rads. And next I'm going to go ahead and apply sine to even indices and cosine to odd indices. So to start with, let's say POS underscore encoding equal to NP of zeros. So I'll start with the zeros, and the things that I want in the diagonals are angle rads dot shape. So that will create my zeros matrix. Next I'm going to say pos of encoding for colon 0 colon 2. For this I will say np. So these are the even indices. I'm going to say np dot sine of angle rads from colon 2 2. So this will just take the even indices. Now for odd indices, I'm going to use cosine. So I'm going to say position encoding, in this case 1 to 2 np dot cos angle rads 1 2. So this will use the odd indices, and then I will return my position underscore encoding back. So this will give me my positional encoding. Next step is to generate the positional encoding, calling the function above. So from that I can see that I need sequence length that we defined as parameter. So I need sequence length, and then sequence length I need embed dimension. I'm going to use embed dimension of 16 this time, and I'll say position encoding is equal to, call the function positional encoding, and it needs sequence length and it needs embed dim. So I'll pass those two parameters. Perfect. So now that I have that, next thing that I need to do is let's visualize this positional encoding. So I'm going to go ahead, say visualize positional encoding using matplotlib. So I'm going to say plot dot figure. Let's create a figure size of 10,6. I have to put it inside parenthesis. Perfect. Next I'm going to say the plot that I want to see is a p color mesh. So p color mesh, use a new one every time we do something, so we can play around with different ones. Pos encoding is what our positional encoding is what I'm going to pass. I'm going to use cmap, so same colors as what we used yesterday. Viridis is what I'm going to use. Next I am going to create the color bar. So call color bar function. Next I'm going to give a title to this. For the title I'll say positional encoding, and then I will, oops, not title, title. Then I'll say plot dot x label. For x label it's using our embedding dimension, so that's what I'll say. And for y label we are using position. So that's good. Now let's go ahead and say plot dot show. See how it looks like. It should be a little bit weird as compared to what you've seen before, because of the way positional encoding works over the entire matrix. So I'm going to say Python day 4, and there you go. We have our positional encoding. Oops, probably and it goes from here 0 to 50 and 0 to 16 here. And as I said, it kind of goes more solid as in when it goes towards right, start from this, and that's how the embedding dimension works. Perfect. So we have this working, this kind of got we got implemented positional encoding. Next thing what we want to do is integrate the positional encoding with a transformer model. So I'm going to close this and go ahead for step 2, where we want to integrate positional encoding with a transformer model. I will use PyTorch. So I'll say import torch. Next, I will import torch.nn as an n. And then I'm going to create a class again for transformer. Day 5, hands-on with pre-trained transformers like BERT and GPT. Today, let's start with introduction to BERT and GPT, some of the very popular ones that you've probably heard. Now, what is BERT? BERT also stands for bidirectional encoder representations from transformers. It's developed by Google AI. It processes input sequences bidirectionally, enabling it to capture context from both directions. It's pre-trained on tasks like masked language modeling, MLM, and next sentence prediction or NSP. Some of the key features of BERT include it's bidirectional, which understands context from both left and right sides of a word. It's transformer encoded based, which means it's optimized for understanding input text. And applications are sentiment analysis, named entity recognition, and question answering. Now, what is GPT? GPT, which stands for Generative Pre-trained Transformer, is developed by OpenAI. It processes input sequences unidirectionally, left to right, focusing on generative tasks. It's pre-trained using causal language modeling. Some of the key features of GPT include its unidirectional, processes text from left to right, focusing on text generation. Transformer decoder based, it's optimized for generating coherent text, and applications include text generation, chatbots, and summarization. Now let's talk about some of the key differences between BERT and GPT. As per the aspect of architecture, BERT is transformer encoded, whereas GPT is transformer decoded. Training objective is MLM and NSP, whereas for GPT, it's causal language modeling. Directionality for BERT is bidirectional and GPT is unidirectional. Use cases for BERT is understanding task example classification, whereas for GPT is generative task, which is text generation. And if you've used ChatGPT, you know what I'm talking about. Now let's go ahead with fine-tuning pre-trained models for downstream tasks. Now why fine-tune? Pre-trained models are trained on large generic data sets. Fine-tuning adapts them to specific tasks like sentiment analysis or classification. Now, what are the different steps to fine tune? First, you load a pre trained model using libraries like Hugging Face to load a pre trained BERT or GPT model. Then, you prepare the dataset, format the dataset for a specific task, example, tokenization for text classification, and then train and evaluate. You fine tune the model using task specific data. So let's try all of this in a hands-on exercise where the objective is to use Hugging Face Transformers library to fine-tune a pre-trained BERT and GPT model for a text classification task. Now, if you don't have not heard about Hugging Face, just Google it, or you can just go to huggingface.co and you'll probably see what it is with all the data sets and models that it has available for you. So first, let's go ahead and create a new file. I'm going to create a Python file, save it as day 5 underscore exercise. And here I am going to first start with installing stuff. So I'm going to open my terminal. And first thing is to install Hugging Face Transformers, you have to say pip install transformers. And I also need the data sets from there. So once you install these, I mean, it will be pretty fast next time. So that's why it's fast for me because I already have it available. Once you have that, now let's import these libraries. Now from transformers, I can import first is auto tokenizer. As the name says, it's used for tokenizing. Next, I'm going to use auto model sequence classification. There you go. Next, I want the trainer, which will train my models. And I need training arguments arguments where I can pass the arguments for my trainer. And next thing I want to do is I want data sets. So I'm going to say from data sets import load dataset, load underscore dataset. That's what I need. So I have everything that I need. So this will install and import the necessary libraries. Now next step is to load and pre-process the dataset. Now we'll use the same IMDb movie reviews dataset that we used before for sentiment classification. So first I'm going to say load the dataset. Now to load the dataset, I'm going to say dataset equal to load dataset, and I specify which dataset I want, db. So this will get me my dataset. Next, I'm going to create my tokenizer. To create my tokenizer, I will call the auto tokenizer that I have imported, and there I'll say from pre-trained, I want to use bird tokenizer, bird base uncased. That's what I want to get. Next, let's go ahead and tokenize the dataset. To do that, I will create a function called as tokenize underscore function, and I'll pass it some examples as argument, and this will return to me tokenizer examples text that it will take, and it will, if you want to pad it, I'll say padding equal to max underscore length and truncation equal to true. If it's more than max length, just truncate the text that is passed to here. Next, I want to get my tokenized data set. So I'm going to say tokenized underscore data sets equal to data set. From my data set, I'll say map tokenize. I'll pass the tokenized function to this, and I'll say batched equal to true. So this will call my tokenized function right here, and then pass the data set from there to it, and then in batch mode it will send that and give me my tokenized data set back. Now next step is to prepare data for training. To do that, I'm going to say tokenized data sets equal to tokenized data set from above. I will remove particular columns, for example text. Next, I will say from tokenized data sets dot rename column. This is some example of what all you can do. You can remove columns, you can rename columns. Now we have labels in here. I want to, or label in here, I want to rename it. So for example, I want to rename it to labels just because I can. Next, I'm going to say tokenized dataset dot set format. The format for this, I want to format as PyTorch. So torch format. Next, I can say train dataset equal to tokenized datasets with training parameters. And for test, I want to use dataset which is inside test. So when you do the above parts, it will automatically give you some tokenized dataset for training and for testing automatically. You don't have to do much. So as you can see, next step is to load the pre-trained model. So to do that, I'm going to say model equal to auto model for sequential from pre-trained. I'm going to pick the model which is bird base uncased. So bird dash base dash uncased. Now inside Hugging Face, you can go and look at all these different things about this model. It will have all the parameters, all the different things that you can do with it. Number of labels that I want to pass is 2, so that's my model is available. Now next is, let's define the training arguments. For training arguments, I'll create a training args variable, and I can call the training arguments. This is where I can pass things like, what is my output directory where I want the training data to be the evaluation strategy. I can give the learning rate, all those things here. So as you can see here, the all the parameters are listed right here. So first is output directory. I'll say output directory. For that, I will save in my local folder which I'm running this file in a results folder. That's where I'll save. Next thing I can do is give my eval strategy. So I'll say eval strategy or evaluation strategy equal to epoch, my favorite ones. And then I'll say learning rate. I can give a learning rate of 2 epsilon raised to minus 5. That's what I can set as my learning rate. And then I can say per device train batch size, I can set that to 8. Next I can say per device eval batch size equal to my evaluation batch size and training batch size, set both to 8. Next I'm going to say number of train epochs, that I can set it to 3. It's going to take a lot of time for this to happen because of the data set that we have. Weight decay, I'm going to say 0.01. Next I can say where do I want the logging. I say logging directory equal to dot slash logs. Next I'm going to say logging steps, how many, so it will print out these to you. So I'm going to say every 10 I want to log it out and also save. And then save steps equal to 500. So that's what I want to save in the logs. So that is my training arguments. Once that is done, next step is to train the model. So to train the model, I'm going to say trainer equal to, call the trainer function that we have initialized or imported, and to this it needs model, which we have model. So I'll pass that. Next parameter it needs is what are the different arguments, the training arguments. I'll pass the training argument that I've created above, which is this one. As you can see, training argument, that's what I've passed. Next parameter is training data set, that I already have created above that, which is training data set. Train data set is what I called it. Evaluation data set, I can set that as test data set. Now if you want to see a better clearly this, I can just move them to the next line so it's clear and visible. Okay, what else do I need to pass here? So I've passed my evaluation data set. Next, my tokenizer, or also called as processing underscore class. It was used to call tokenizer before. So if you're familiar with that, that's what. So if you see that it still shows up over there, tokenizer. So that's called processing class in the latest version. If you give, I think tokenizer. So if you give tokenizer equal tokenizer, it might give you a warning saying that it is deprecated and you would want to change it. You can try that out. And then I'll say train dot train. Now this will take forever to train because of the data set that we are passing. So I am going to go and do the next steps too. So next is evaluate the model. To evaluate the model, I'm going to say results equal to trainer dot evaluate. I can just call that function. That's it, that will evaluate it, and that I can print evaluation results from my results above. Perfect. So that will give me my evaluation results. Next, if you want to experiment the same thing with the GPT, I can probably write the code here. So I'll probably say experiment with GPT, because one is large enough, you don't need another one. I'm going to comment this code out, but for this I'll say transformers import auto model for causal LM. So that's the one. As I mentioned, your GPT uses causal language model, and then load the pre-trained GPT. I can just say GPT underscore model equal to auto model for causal LM, and from pre-trained I can pick GPT-2 in this particular case. Then I can say input underscore text equal to once upon a time. That's my input text. My input underscore IDs equal to tokenizer that I've created above dot encode input text that I've created above once upon a time, and my return tensors in this place is PyTorch PT. Next, I can say output should be GPT model dot generate. I call generate function, and I say input underscore IDs comma max underscore length equal to 50, and number of return sequences that I want for this sequences equal to 1 is good enough for us. Number of return sequences, trying to make sure there's no typo, and then I can print this out saying print generated text equal to, I'll pass the tokenizer dot decode, and to that I'll pass output, whatever I get back, output at 0. And I'll also say there's one thing special, there's sometimes there's some special tokens in front and back, so I will say skip special token equal to true. Okay, perfect. So this kind of takes care of everything. I'll probably also run this along with it just to see what happens. Doesn't matter, but it's going to take a lot of time. So I'm going to go ahead and first start this process, Python day 5. It's going to run through it. It's going to take some time. Let's see. First, it will try to get the library data sets and stuff. And there you go. It started the process of downloading. It will first get the samples data, and all my examples have been downloading. It will do this, I think, 3 times first, where it gets all the data. Next, I mean, it says some weights of bird classifier were not initialized, so I don't, that those are just warnings. You should probably train this model on a downstream task to be able to use for prediction. So that's what it mentions, but here is where I am doing all the things. Now, as you can see, since I mentioned that I want to do every log the steps every 10 steps, so every time it finishes 10, so 17, 18, 19, 20, it will print. And as you can see, it has 9375 and is doing 1 per second pretty much, or a little bit slower than that. So it's going to take around 3 hours, I think. So I'm going to leave it here right now, and I'll come back, and when it's done, I'll show you the output. So it took around almost 5 hours, I would say, to run through those 3 epochs and give us some output back for this. Now, as per the BERT model goes, we, as you see here, it ran through all the different epochs, 3 epochs, and took around 3 hours and 51 minutes, and then it went through each and every one of those epoch items, and then kind of got us the evaluation results. Our evaluation loss, as you can see, is 31%, and evaluation runtime, this is the runtime that it took. Samples per second, these many samples were evaluated per second, and epochs are 3. We also wrote some code for this GPT, which is not completely complete because I did not give attention mask and bunch of different things, which we'll probably be doing tomorrow. But it says that the attention mask and the pad token ID were not set. As a consequence, you may observe unexpected behavior. Please pass your inputs attention mask to obtain reliable results. And also says setting pad token ID to EOS token ID, none for open-end generation. So it will try to do that, but as a result, as you can see here, the generated text that we get is once upon a time, unused. So it's trying to fill it up, but it can't get the actual data out properly. But we were able to fine tune a pre-trained BERT model for the text classification. We also evaluated the fine-tuned model performance using the accuracy of the metrics. And finally, when we try to explore the GPT's text generation capabilities, since we didn't even put the code or completely write the code, we'll probably do this more on the next session. So I hope you were able to get these results similar to this. If not, let me know in the messages and I'll get back to you. To summarize, today we understood the differences between BERT and GPT, including their architectures and use cases. We learned how to load and fine-tune pre-trained transformer models, for specific NLP tasks, and we gained practical experience using Hugging Faces Transformers library. And finally, we built foundational skills for advanced application like custom fine tuning and transfer learning. If you have any problems or had any questions or issues, let me know in the messages and I'll get back to you. Day 6, Advanced Transformers, BERT variants, and GPT-3. So let's look at exploration of BERT variants first. Why BERT variants? While BERT is powerful, it has limitations like large computational requirements and inefficiencies in capturing certain nuances. BERT variances optimize the model for specific tasks, improve performance, or reduce computational overhead. Some of the key BERT variants include Roberta or robustly optimized BERT. It removes next sentence prediction NSP task for better efficiency. It trains on more data with larger batch sizes, and use case can be superior performance in tasks requiring deeper context. Then we have digital BERT, a distilled or smaller version of BERT that retains 97% of BERT's performance while being 60% faster. Use case is ideal for real time applications and resource constrained environments. Then we have Albert or a little BERT, reduces memory consumption by factorizing embeddings and sharing parameters across layers. Use case is suitable for large scale pre trained and downstream tasks with memory limitations. Next, we have BERT Wheat. It's fine tuned on Twitter data, and the use case is social media, sentiment analysis, and hashtag prediction. Next, let's go into introduction of GPT-3. What is GPT-3? GPT-3 or Generative Pre-trained Transformer 3 is developed by OpenAI. It's a massive model, 175 billion parameters trained on diverse data sets, and it excels at generating coherent and contextually relevant text. Some of the key features of GPT-3 include zero shot and few shot learning, which can perform tasks with minimal or no fine tuning. Versatility. It's used for text generation, summarization, question answering, and conversational AI. Some of the applications include first conversational AI, where chatbots and virtual assistants. Next is content generation, like articles, scripts, code snippets, and creative writing, like poems, stories, and creative ideas. Transfer learning in NLP with transformer models. Now, what is transfer learning? Transfer learning involves retraining a model on a large dataset and fine tuning it for specific downstream tasks. Advantages include it reduces the need for task specific label data and speeds up training and improves performance on specialized tasks. Now, with all the knowledge that we gained, let's get into our hands on exercise where the objective is to experiment with the BERT variant. Example is Roberta and fine tune it on an NLP task. We'll use the GPT-3 API for text generation and analyze the quality of the generated text. So let's get started. So to start with, let's go ahead and create a new file, Python file. I'll save it as day 6 underscore exercise 1 or exercise. And then here, first, let's get from transformers. I am going to import our auto tokenizer, and I will also import the auto model for sequence classification. So I'll say auto model for, let's write it down, for sequence classification. That's the next thing that I want, and I want oops, trainer and the trainer arguments, training arguments. There you go. So these are the basic ones that we used earlier too. So next, for data sets, I'm going to say from data sets import load dataset function, and with that available, I'm going to go ahead and load my data set. So for that, I'm going to say data set. In this particular case, I am going to load my data set, which is called AG news, AG underscore news, and I will load the Roberta tokenizer and model. So say load Roberta tokenizer and model. And I'm going to say for that I'll create a variable called as tokenizer, and to that I will say auto tokenizer dot from pre-trained. I am going to get, as I mentioned, that is available at Roberta dash base. So if I show you here, so Roberta dash base, that's where you can find the Roberta tokenizer. Next, for the model, I'll do the same thing. I'll say model equal to auto model for sequence classification dot from pre-trained. I want to get the same one called as Roberta dash base, and I'll give another for labels. I'm going to say number of labels that I want is equal to 4. So specify that. So I have my model and my tokenizer. Next thing is, let's go ahead and tokenize data set. For that I'll write a function as before, tokenize data set, and here I'm going to create a function called as tokenize underscore function, and it takes inside argument, let's call it examples, and here I am going to say return. So this will return using the tokenizer. So as a tokenizer, I'll pass the examples, which is inside has labeled text, comma. Then I'll say truncation. So if I want to truncate something based on the max length, I'm going to set that to true, truncation. Next, I need the padding of how much padding if the max length is not reached. I'm going to say max length. So based on max length, it will do that. And what is my max length? I'll have to also provide that. I'll say 128. So that will give me my tokenized items. Now let's go ahead and say tokenize underscore data sets, and for that I'll say data set dot map, and from there I'll pass that function that you created, tokenize function, and it wants to know if it bashed or not. So I'm going to say bashed equal to true, set it in batches. So that's done. Next step is to prepare the data set. So I'm going to say prepare data set. Inside here I'll say tokenize data sets or tokenized data sets, just so be more precise, because these are my tokenized data sets. I'm going to say tokenized data set dot remove columns. I am going to remove the column called as text inside here because they are tokenized already. And then I'm going to rename the label as labels. So I'm going to say tokenized data sets equal to tokenized data sets dot rename column. One column I want to rename, so that's why. And then I'll say labels, label to labels. So that's good. Next thing I'm going to say tokenized data sets dot set format. Now what format do I need to set here? In which torch? PyTorch. So that's why I'll say torch. Next thing is I need after once I select torch, next thing is I want to get the train data set. So I will say train data set for the model. This is for the model that I can get from tokenized data sets, and once with the label train. Same thing for test data sets. This will be available inside my tokenized data sets named as test. So perfect. So I got that. So next, let's go ahead and get the training arguments. Training, too many in arguments, and those are, I'll call it training underscore args equal to training arguments, and inside that I'll pass the parameter that it needs is first is output directory, is where you want to output. I'm going to say dot slash results. Next I'm going to say what is the evaluation strategy that it needs, or eval strategy is equal to epoch. Next we need is learning rate. What is the learning rate? So this I'll say 2e minus 5. Next I want to say per device train batch size equal to 16, and then I'll need per device eval batch size equal to 16 again. Next I need is the number of training epochs. So I'm going to say number of train epochs equal to 3. It's quite a lot. It's going to take 4 to 5 hours. Weight decay equal to 0.01. I always say once you run this, what you have to do is you just go ahead and do rest of the stuff of your day and then come back. And then I'll say save steps every 500, save a step. Weight decay is 0.01, number of train epochs 3. So everything is ready for my training arguments. Now it can be taken by trainer. So let's create our trainer here. Trainer, I'll say trainer equal to trainer, and to this first thing it needs is the model. So I'm going to say model equal to model. That's what we named it, so easier. Next it needs the arguments, which is the training arguments. So I'm going to give it whatever I created above. So I called it training args. Next it needs is the training data set. So I'm going to say train data set equal to, I called it train data set. And then next is eval data set. So eval data set equal to, I called it test data set. And then next it needs the tokenizer, or which is also called as processing class, if I'm not wrong, equal to tokenizer. It still thinks is tokenizer. This is what do you call it, deprecated. Before it was called tokenizer equal to tokenizer. Now it's called as a processing class equal to tokenizer. So that's how you set it. Now once this is done, let's go ahead and train our model. So train this model. Let's train our model. To do that, I'm going to just say trainer dot train. That's about it. Now since it's going to run 3 to 4 hours, let's also go ahead and get the evaluation results. So evaluate the model, and I'm going to say results equal to trainer dot evaluate, and then I'll say print evaluation results is equal to results, whatever I got above. Save it. So this should be good to run. Now again, as I mentioned, once I run this, it's going to take 4 to 5 hours. So be prepared for that. So I'm going to go ahead and say Python day 6. Okay, let's run it. Now as I mentioned, it's going to take some time. So I'm going to let it run and then come back when it's completed training and then evaluating the data, and then we can continue from there. So it took around 4 to 5 hours, I think, approximately, to get this thing running, and we have our results here based on the data that we have provided, the AG news set, and using our model, we kind of got the evaluation results here. The final evaluation results say evaluation loss is 20%, whereas evaluation runtime is 72.13, samples per second is 105, and steps per second is 6.5 with epochs of 3. So this is our final results here of the evaluation. I hope you are able to follow along and get some similar results. Our next step is to use the GPT-3 API for text generation and analyze the quality of the generated text. So let's go get started with that. So let's go to Visual Studio Code again, and this time I'll create a new file. I'll save it as, let's call it day6ex underscore OpenAI. And to run this, first what I'll have to do is I'll have to install OpenAI. So I'm going to say pip install OpenAI. So they have a library available. So it's very fast for me because I've already installed it, but make sure that you install it again. And once you have that installed, let's go back here and write our code. First I'll say import OpenAI. Next I'm going to set OpenAI API key. So for the OpenAI API key, go to Chrome and go to platform.openai.com and create an account, and inside there you can get your API keys from API keys here. I've already created an API key, and that's what I'm going to use. Do not use mine because again, it's built and it will be built to you depending on how much you use. So do not use mine, and I'm not going to show you mine, but this is where you get the key from. So when you say create new secret key, it will show you your API key and you can use that API key. So I'm going to close this here. I'm going to go here. Our next step, as I mentioned, is to set this up so that I say open AI dot API underscore key. That's how you set it. And here you set your key. Now I'm going to just copy my key into here. Next, I'm going to say try. And first thing I'll try to do is I'll try to generate text using, I'm going to use GPT 3.5 Turbo that's available to me. So I'm going to say I'm going to use that library. For that, I'm going to say response that I get from the API equal to OpenAI dot chat completion dot create, and inside here I will set first the model that I want to use is, as I mentioned, is GPT. Actually that's in double quotes. I'll say GPT dash 3.5 dash turbo. Next I'm going to say what is the message that I want to send. So I'm going to create an array of messages equal to give it some context. I am going to say the first one where the role, so I have specified as a key value pair where the role is system, and the content of this is, it says you are a helpful assistant. That's what I'm going to say, and that's the role for the system. Next we have, I'm going to create a role called as the user who's going to ask questions. User, and his content is, I'm going to say that write a short story about, you can like specify as if you're going to chat GPT and saying stuff. So you can say about a robot learning to cook, something like that. So that's what I'm asking it to write. It's saying, think of like as if you're going to chat GPT and writing this text, what will happen. So it will do the same thing because again it uses the same OpenAI engine. So next step, so that's the messages that is passed. Now I'm going to say max underscore tokens used for this is 150, and then I'm going to say temperature. So temperature is used to check like how much how, like, more higher the temperature better the answer is, but it's cost more too. So that's what I've specified here. Next I'm going to go ahead and print my generated text. Generated text is, I'm going to move it to next line and say from the response. So you can look at the documentation. So the response comes in an array list called as choices, and inside that I'm going to pick the first choice, and from that first choice I'm going to read the message in there, and that message object has another object inside. It's not p but content. So that's where the data is. So from that data I am going to go ahead and say strip, because it might have some spaces and other things. So I'm going to strip it out. So strip will clean the text that I have and display it for me as generated text. Next, now I have given try, so I'm going to also say except. So that means if there's an error or something, if there's an exception, I want to catch it instead of crashing. I'm going to say print here f of an error occurred, and that error, if I want to display it to the user or here on the screen, I'll display that error. So perfect. So my entire code is here. So this is how it works. It just to replace your OpenAI API, get that, and then you can run this too. So I'm going to go ahead and run this. It will be faster, not doesn't take 3-4 hours. It'll be immediate because the API is already, the AI is already trained, the model is trained. All I'm doing is passing a question and it's going to give me a response. So I'm going to say Python day 6 underscore OpenAI, run it. And there you go, we have the generated text. Once upon a time, in a bustling city filled with technology and innovation, there was a robot named RoboChef. RoboChef was a state of the art robot designed to assist in the kitchen, but there was one problem: RoboChef couldn't cook. Determined to learn, RoboChef embarked on a journey of discovery. It started by observing the talented chefs at a nearby restaurant, studying their every move as they chopped vegetables, stirred sauces, and grilled meats. RoboChef also read countless cookbooks and watched cooking shows to understand the art of culinary creation. After weeks of learning and practicing, RoboChef decided it was time to put its newfound skills to the test. It gathered ingredients and set up a cooking station. And it stopped. Why? Because I said tokens equal to 150. If you specify more, it will give you more data, but again, it will cost you more too. Same thing with temperature. So there you go. We have completed both our exercises. I hope you were able to follow along. If you have any questions, let me know. So just to summarize, today we explored the strengths of BERT variants like Roberta and their advantages over BERT. We understood the capabilities of GPT-3 for generative tasks and its limitations. We learned to fine-tune pre-trained models for specific NLP tasks using Hugging Face, and we built some practical skills in working with state-of-the-art transformer models. If you have any problems or issues or questions, let me know in the messages and I'll get back to you. Day 7, Transformer Project, where I'm going to guide you through text summarization and or translation. You can pick one or both. Let's start talking about applying transformer based models to advanced NLP tasks. Our first task is text summarization. That is the process of condensing a piece of text while retaining the key information. There's two types: extractive summarization, which selects key phrases or sentences from the original text. And then we have abstractive summarization, which generates new sentences that capture the meaning of the original text. Next, text translation, that converts text from one language to another while maintaining the meaning and grammar. Examples can be English to French translation, multilingual translation with models like T5 or MT5. Let's talk about fine tuning and optimizing models. We have pre trained models for summarization and translation. First is T5, which is text to text transfer transformer. That's why it's called T5. It treats every NLP problem as a text to text task. It's fine tuned for summarization and translation tasks. We have BART, which is bidirectional and auto regressive transformer. It combines BERT like encoder and GPT like decoder. It's pre trained for denoising and fine tuned for summarization and translation. Next, what are the optimization techniques? Learning rate scheduling and hyperparameter tuning, where you tune the batch size, optimizer type, and maximum sequence length. Let's talk about analyzing model performance next. So, what are the different evaluation metrics for text summarization? We have ROGUE, which is recall oriented understudy for gestling evaluation, and we have BLUE, which is bilingual evaluation understudy for generated summaries. Next, for text translation, we have Blue score for translation quality, and we have Perplexity to measure model performance. With this in mind, let's jump into our hands-on project where the objective is to fine-tune a pre-trained transformer model, example T5 or BERT, for text summarization and or translation and evaluate its performance. So let's get started. So first step, let's go ahead and create a new file. I'm going to say Python file, save it in our day 7 underscore exercise. And then first thing that I need to make sure that you have all the install required libraries. So I'm going to go ahead and say pip install transformers and datasets. So make sure you have this. It will be pretty fast if you do that early. Next step is to prepare the dataset. Now we will use the CNN Daily Mail dataset for summarization, and for if you want to do translation, you can use the WMT 14 English French dataset for translation. And I'm going to show you the steps as I mentioned. So I'm going to say from dataset import load dataset. So this will load my datasets. Now to load the dataset for summarization, I'm going to say dataset equal to load underscore dataset and pass it. As I mentioned, I'm going to use the CNN underscore daily mail, and the version is 3.0.0 is what I'm going to use. And then I can print of how this dataset looks like. Dataset in the training module, show me item number 0, just to see how it is. Now, for translation, you can use, I'm going to create this variable, but I'm going to comment it out. You can run this yourself. Data set, and as I mentioned, the best one to use is WMT14 at the time of the recording. There might be better ones coming out, but this is what I'm going to use, English to French. So that's what you can use. I'm going to comment this out because I'm just going to do summarization right now. So now next is we have to tokenize the data set, which we have done before. So for that, again, from transformers, I need to import auto tokenizer. If you spell wrong, then it will not help you. Auto tokenizer. Next, I'm going to go ahead and first load the tokenizer. Now the tokenizer in this case is, I'm going to use the T5 small tokenizer. So I'm going to say tokenizer equal to auto tokenizer, and from underscore pre-trained, I'm going to, as I mentioned, T5 dash small. That's what I'm going to use. Next, I'm going to say tokenize for summarization. I'll do that. I'm going to move this up a little bit so it's available. Function is, as I mentioned, tokenize underscore function. This will be added as a parameter in the actual tokenizer that I'm going to call in some seconds. So function examples. Now first, I'm going to say inputs equal to summarize, and then I'll pass it doc for doc in examples. So I'm going to take the example that was passed to me. Inside that, I have articles, which is articles from the CNN, this one data set that we have, CNN Daily Mail. It takes these articles and it will take each and every one as a doc and then summarize them. So that's what it does here. Next step is, I'll say model underscore inputs equal to tokenizer and pass it inputs that I've created above, and I'll say max underscore length equal to 512. That's the max that I want to do, and then truncation equal to true. So that's my model inputs. Now let's go ahead and tokenize the targets. To do that, I'm going to say with tokenizer dot as underscore target tokenizer. I want to get the labels, which is equal to tokenizer, and it needs examples of highlights. So these are my targets. Max length equal to 150, and I'll say truncation equal to true as before. Perfect. So that takes care of my tokenizing targets. Now let's go ahead and I'm going to say model underscore inputs dot labels equal to labels of input IDs, input underscore IDs, that's where it is. And then I will finally return my model inputs. Perfect. So that's what I'll get back. Next step is to fine tune the model. So for that, I'm going to go ahead and first from transformers, or I can just use it here. I can say auto model for this time. I'm going to say use sec to sec, sec to sec lm. That's what I'm going to use. Go at the bottom here, and I'm going to say model that I want to use is auto model sec to sec lm dot from pre-trained, and I will select, as I mentioned, T5 dash small. Next, let's go ahead and define the training arguments. So I'm going to say for that, I will go above, and in here from transformers, I need training arguments, as you remember. So I'll go back, and here I'm going to say training underscore arguments equal to training arguments, and here pass the different arguments. Now it will help me here to tell me what it needs, which is output directory equal to dot slash results. So it will create a results folder over there, and that's where it will keep the results. I want to say the evaluation strategy, or eval underscore strategy, that I want to use is epoch. Next, I'm going to say that the learning rate that I want to use here is 2e dash minus 5, and then I'll say per device eval batch size and train batch size equal to 8. So I always like to give per device train batch size equal to 8, and then eval batch size equal to 8, and then I'll say number of training epochs that I want to do is equal to 3, and then I'll say that weight decay that I want equal to 0.01, and then I'm going to say save the total limit equal to 2, and I'll say predict with generate, which is predict with generate equal to true. Maybe because I messed up something above. Let's go ahead and fix this. Weight decay equal to 0 point, and then predict with generate equal to true. Perfect. So these are my training arguments. Next thing that I want to create is to train the model. Now to train the model, I need to get the trainer. So I'm going to go above here, say trainer. Now here I'm going to come down and say that trainer equal to trainer, and then pass it model equal to model arguments equal to training argument that I've created above. Next, I will say training data set that I want to use is my tokenized underscore data set. Did I create that above? I guess I forgot to create the tokenized data set after this step here. So I'm going to say tokenized underscore data sets equal to data set dot map, and to this I pass that function above that we created, tokenized function, and then I say batched equal to true. Okay, perfect. So now that I have tokenized data sets, I can go here and say tokenized data sets of train. So that will get my train data set. Next thing I want to do is get the evaluation data set. So that is eval data set equal to tokenized data sets again, and this time the value is inside not test, but it's called validation. Next thing that I need is my processing class, or also called as tokenizer. From before is tokenizer. I say that's fine. So before it was called tokenizer, that's why it says tokenizer equal tokenizer, but we need process. The new one is called, it will still work, but it's better to give the new name because that will be deprecated eventually. Then I'll say trainer dot train. This will train the model. It's going to take some time, so you can relax after that. So next, before even stopping, we want to see it in action. So what I'm going to do is I'm going to give a sample text. This is the evaluating the model. So I am going to say sample underscore text equal to, I have some sample text, let me get that. Now paste it here. So the transformer model has revolutionized NLP by enabling parallel processing of sequences. That's my input text. Now I'll say my inputs equal to tokenizer, and then to that I'll pass summarize, and I'll say what do I want to summarize here, plus sample text from above. That's my input. Next, I'm going to say return tensors, return underscore, come on, show me tensors equal to in PyTorch format. So that's why I'll say PT here. Next, I want to specify the max length. So max underscore length equal to, I'll say 512, and then I'll say truncation equal to true. That means if it's more than what I need, I'll truncate it. So perfect. So that's done. That's my inputs. Now let's go ahead and get the outputs. Outputs equal to, I'll call the model and say generate and to this I'll pass the inputs of input IDs, input underscore IDs, and then I set max underscore length equal to, set it to 150, same as our GPT that we did yesterday. Next, I'm going to say number of beams. In this particular case, I want to use 4, and I want to say early underscore stopping is true. So this can stop early equal to true. Perfect. So that will take care of my outputs. Now that I have inputs and outputs, let's go ahead and print generated summary. So based on whatever text, sample text I have provided, let's see what does it give me. So inside my tokenizer, I have that decode function which I can run here, and to this I'll pass outputs at 0. I will say the next parameter is skip underscore special token. So if there is some special variables that are created or that helps the model, so that I'll say skip them, don't show me, I don't care about them. That's what I'm pretty much saying here. I just want to see the text here. So if you also want to evaluate using Rogue or Blue, what you can do is you can say metric equal to load underscore metric, and then pass here Rogue, ROUGE, or you can use it's also called, for Blue you can say SACREBLEU. So that's what you can use for that. That's what you can specify, and then you can say predictions equal to outputs of, in here in this case, generated underscore text, and then you can say references equal to data set of validation, and then highlights, HIGHLIGHTS, highlights. Okay, so and then you can replace this with the target translation for translation task, and then if you want to get the results, you can say results equal to metric dot compute, and then to that you can say predictions equal to, pass the predictions that we got above or created above predictions, and then it needs references which we have created above references, and then finally you can print the final evaluation metrics by just saying, let's say, like you can just say results, and this will give you the what do you call the evaluation metrics over here. I'm going to go ahead and comment this out because I just want to see the generated summary and I don't want to see this. So let's go ahead and run this and open my terminal and say Python, and the name of the file is day 7. Okay, there you go. And it started reading getting the data, and then it's going to run for a little while. So I'm going to leave it as it is and come back once it's completed training and evaluating and show you the final output. So it took a couple of hours, but after that we got the generated summary where it says transformer model has revolutionized NLP by enabling parallel processing of sequences. So we were successful in training or fine-tuning a pre-trained transformer model. In this case, we used T5 for text summarization and were able to look at the outputs. If you had any issues or problems with implementing this, let me know and I'll get back to you. Now to summarize, this week and today, we understood the end-to-end workflow for fine-tuning transformer models on advanced NLP tasks. We gained hands-on experience in data pre-processing, fine-tuning, and evaluation for summarization and translation. And we learned to experiment with hyperparameters to optimize model performance. We also developed insights into practical challenges and solutions for working with large-scale NLP tasks. Let me know if you had any problems, issues, or have any questions in the messages, and I'll get back to you.